All right, chapter 12. This chapter is not very long. The information is not involving a lot of math or anything, so this should go by pretty quickly. Thank you for bearing with me. So, what we're going to talk about in chapter 12 are liquid solids and intermolecular forces. So, let's start to break down that word intermolecular forces. Now, if you are an if you have like a learning style that's like interpersonal, that means that you learn better in groups with people. Okay, so inter meaning between. Okay. Now, another word or another prefix is intra. Intra means within. So if you are an intrapersonal person, then you learn by yourself. You kind of look within, you'll journal more, or you kind of get in your own head about stuff. So if you're interpersonal, you like to be between other people, you like to talk to other people outside of yourself. If you're intrapersonal, you are better at like studying by yourself or working alone. So we're going to be talking about intermolecular forces. So these are the forces that exist between molecules. We've already talked about some intramolecular forces within molecules. So what kind of forces have we talked about that exist inside or within molecules? So you've got the force of an ionic interaction. Right? And an ionic interaction is this electrostatic attraction. Not really a bond. I'm not going to say bond. Your book will say bond, but I don't like that. Electrostatic attraction is not a bond. It's an interaction between positive and negative charges in that ionic molecule or that ionic formula unit, that ionic compound. That is intra. That is within the molecule. What else? Covalent. So a covalent bond, right? This is the sharing of electrons that's happening inside the molecule, within the molecule. These are very, very, very strong forces. Okay, so these forces are than um, stronger than the intermolecular forces. So we're now talking about things that are a little bit weaker than bonds or ionic interactions, but they still exist, these forces, and they help us out a lot by making water the way it is, for example. So let's move on to the next slide. Um, so uh, one of the things we're going to talk about in this chapter as well is called thermal energy. You've already talked about thermal energy. We've talked about enthalpy. We've talked about enthalpy of reactions. So thermal energy is really just the energy of this constant motion of particles. So in the last chapter, we talked about how kinetic energy is directly proportional to the temperature, right? So this movement of particles, okay, this constant motion, this restlessness of particles is its thermal energy. And that increases the temperature, but thermal energy and temperature, heat are not the same. And so thermal energy is this just constant motion of particles that create this kinetic energy. So it's related to the kinetic energy. Gases, liquids, and solids all have different thermal energies, right? Because they have different kinetic energies. So which one do you think has the highest thermal energy? Right, so gases have the highest thermal energy just simply by the fact that they're moving a lot faster, right? They're moving faster, they've got more space to move. Yes, you can have a gas that's colder, I guess, but if you're talking about the same substance, the gas will always be warmer than the liquid or solid version of that substance. Just look at water as the best example. So like water vapor, steam is way hotter than water liquid. Even if it's close to boiling, the steam is still hotter. It's still at a higher temperature. And then, which is much hotter or at a higher temperature, more thermal energy than a solid, because the solid particles are not moving very fast. They don't have a very high thermal energy. So this has the highest thermal energy. And so this thermal energy, this constant motion, this movement, the space that's allowing the movement, right, makes solids, liquids, and gases um, behave in different ways and take on different properties, including their shape. So if you put a liquid into like a flask, it's gonna make the shape of the flask, right? The liquid is gonna now be in the same shape as the flask. But if I were to take some ice and try to stuff it into the flask, it's not going to automatically take the shape of the flask. Right? Ice has its own crystalline structure. Do you see the structure here? This is really important. This structure actually makes ice float on water. It's less dense. It's one of the very few solids that we know of that actually the solid is less dense than the liquid because of this crystalline structure. It's because of these intermolecular forces we're going to talk about later that cause this structure to happen. Um, so this is really important concept that seems very simple to us. Oh yeah, like ice floats, but it's the reason behind that is also the reason why like DNA works and everything else. So we're going to look at the intermolecular forces. I'm going to call them IMFs and the different properties. So what is the property you think that's discussed in this or looked at in this picture here? There's a paperclip. It's floating on this water. So this is going to be the property of water to have this surface tension. Okay, have you ever seen the little bugs that like float on top of the water? They look like they're like walking on the water. These bugs are using surface tension of the water. Now, surface tension of the water is because the water particles are attracted to each other, right? They are held together. And so we'll talk about why they're held together in just a second. But the water particles have this attraction. They're interacting with their neighbors, and so it's creating this like chain kind of that's holding the paper clip on top of the water because these interactions are really strong. So viscosity is another property. So viscosity is just how fast something moves, like down a slope. So imagine you had like a pan, cookie sheet maybe, okay, and you had it kind of resting, and you were to put some samples of some liquids on it, and you were to see how fast they made it down the pan. Okay, so if you put something on it, like if we put some oil on the pan, if we put some syrup on the pan, if we put some honey on the pan, like how fast would they move, right? That's how viscous they are. So if they're more viscous, they actually move slower. So a viscous substance would be like honey is very viscous. It's kind of thick. The water is not very viscous. It flows pretty freely, right? So this has to do with the interactions between the particles. And the interactions not only between the particles, but the interactions of the particles to other things they're like sliding down, right? The honey might move really quickly through the air, but like it's sticking to the bottle and it's sticking to the pancakes or it's sticking to the your hands, right, or your spoon. So that interaction between not only the particles of the syrup itself or the honey itself, but the interaction between the particles of the syrup to whatever substance it's touching as well. That can explain viscosity. Okay. Evaporation. We all know what evaporation is. Evaporation is just going from liquid to a gas. Now, if you are held very tightly together, you're going to be much harder to evaporate, right? So if these particles of water are held together very tightly, we know that because we know about this surface tension, right? If the particles want to jump out and become gas, they've got to break that interaction. They've got to break free of that bond. So if you have this graph is showing us the kinetic energy and then the fraction of molecules that exist at lower, higher temperatures. So if you increase the kinetic energy, you get this fraction of molecules that are going to be at a higher temperature, which means you get more that are going to reach that minimum kinetic energy to escape that liquid form. Okay, if you're at a lower temperature, you got more molecules of this lower kinetic energy, right? But I have less, let me do a different color. I have less particles that are going to be jumping out of the liquid water, right? Because they don't have as much kinetic energy. Think about like dolphins jumping out of the ocean, right? You gotta have kinetic energy if you want to jump out and become a gas. Condensation is the exact opposite, right? So if you really have a good attraction to your neighbor as a liquid, well, you're going to want to become a liquid easier. So you will need less prompting to become a liquid. So whatever property you have as far as evaporation is concerned, the opposite is true for condensation. So if you're very difficult to evaporate, you're very easy to condense. Vapor pressure we've talked about before. Vapor pressure is just the pressure of the gas or the vapor that's on top of a liquid at any given temperature. Boiling. Boiling is a little bit different. We use it the same as evaporation, but it's a little bit different than evaporation. Boiling is when you get these pockets of gas because the bottom of the container is hotter than the top of the container. That's true when we're cooking something, right? The bottom of the container is where the heat's coming from. So you've got particles on here that are becoming gas, not up here becoming gas. So the big gas pockets float up because they want to escape out as a gas. They're trying to get out of the liquids. That's what boiling is. It is evaporation, but the evaporation's happening like inside the container down at the bottom of the pan or the pot, and then it's like drifting up. So it's a little bit different than if you just like sat some water outside and the sun evaporated it because the sun is heating it from the top down. A boiling is heating from the bottom up. So it's a little bit different. Thinking about boiling and evaporation, and we call it the same thing, but it's really not the same thing. So you're going to see this also in your book as a heating curve. Heating curves are really simple. It's just as I add some heat, okay, the temperature is going to increase. That makes sense, right? If I add heat, I put something under a Bunsen burner, the temperature is going to increase. Now that makes sense for most of this graph. So let's look at this graph. Let's start down here. So I've got this, we're starting out as a liquid. Actually, in this heating curve, in this picture right here, we're starting out as a liquid. So I'm at 20 degrees Celsius, and I'm heating. The temperature of the liquid's getting higher and higher and higher. Then I hit 100 degrees Celsius. And if you know about water, you know that 100 degrees Celsius is the boiling point of water. So as I hit that boiling point, something interesting happens. I'm adding heat still, but my temperature is not changing. This is when I'm boiling. This is my boiling point. This is when I'm boiling right here, or when I'm evaporating. But I'm adding heat, but my temperature is not changing. That doesn't make sense, right? This part of the graph makes sense. Adding heat, temperature increases, great. I get that. But you're adding heat, and when you're boiling water, you can sit there and let it boil and boil and boil and boil and boil, and it will never get above 100 degrees. Like, you don't believe me? Try it. You have to take a thermometer and stick it into some water. It will never get above 100 degrees unless you've got some other contaminants in your water. But if you're using pure water, it won't get above 100 degrees because at this point, you cannot have liquid water above 100 degrees C. Once you get above 100 degrees C, you're not liquid anymore. Right now, you're gas. So what's happening in this part right here where this weird section where I'm adding heat but my temperature is not changing? I must be doing something else. So what you're doing is you're actually overcoming these forces. So we're going to talk about in just a second these forces that are holding the water molecules together, right? So when you're heating up the liquid, you're actually separating, you're making the particles move faster, okay? Because temperature, remember, is just the average kinetic energy. So I'm making the particles move faster, making the particles move faster, and then I get to this point where the particles aren't moving any faster, but I'm still adding heat. That heat is going into breaking apart these interactions between molecules, these intermolecular forces. So we're breaking down these intermolecular forces so that all of my water molecules can turn into gas, because we talked earlier about the difference in solid liquids and gases. Liquids are very close to each other, solid gases are very far away, so you need to actually pull it apart. So this section right here is the heat required to pull apart all of the liquid particles. We call that the heat of vaporization. There's also a heat of fusion. So vaporization is liquid to gas, fusion is solid to liquid, but the same thing happens. So if you look at a heating curve of full like solid to gas water, you'll have two places like this. It'll look like this. Okay, you'll have two places. This is your heat of fusion. This is your heat of vaporization, where you're flat. Okay, this is where you're breaking apart these interactions between molecules. So I can use this. Look at this beautiful unit, kilojoules per mole. You know what that means. That means we're dealing with a conversion factor, my favorite thing. So we can use this. Okay, so look at this question. Calculate the amount of ice in grams that upon melting at 0 degrees C absorbs 237 kilojoules of heat. The heat of fusion for water is 6.02 kilojoules per mole. Okay, I want grams. I'm melting this ice. It absorbs 237 kilojoules because it's endothermic, right? I need to take in energy to melt the ice. The heat of fusion for water is 602 kilojoules per mole. Well, I see I have kilojoules here, but I want grams. So I'm going to need something else, right? So I know that water is actually 18.02 grams equals 1 mole of water. They tell me ice. I need to know that ice is water, H2O. So I can use this conversion to get some moles. So let's start with our 237 kilojoules. So we're going to use our 6.02 kilojoules down here. 1 mole up top. 1 mole on the bottom. 18.02 grams here. And this will give us the amount of ice that absorbs 237 kilojoules of energy. And I typed that in wrong. 237 divided by 6.02 times 18.02. 709 grams of water. You can say solid or you can say ice. Okay, that's how you use these. That's how we just deal with them. So anytime you see two units, remember you can use the conversion factor and we can use it as a place to get where we need to go. Alright, now we're going to talk about these intermolecular forces, these IMFs. So there are 3 different intermolecular forces that we need to know. We're going to discuss them. Just a really quick recap. Intramolecular forces are bonds and ionic interactions. Intermolecular forces are between molecules. We have not talked about this yet. This is new. This is old. This is new. Okay. The first one is called dispersion forces. So dispersion forces are or called London dispersion forces. You can also maybe see they would be called van der Waals forces. But they're the weakest attractions that we're going to talk about today. And they are kind of hard to explain without showing you, but I'm going to try to use these pictures here. So let's just say that I am this helium atom. These are 3 helium atoms together. Now we know helium is not bonding with another helium atom, right? So let's just assume for a second that these helium atoms are hanging out. Now they're not bonding, right? But they do wind up having interactions between these atoms, but they're not intramolecular because they're not bonded, so they're intermolecular here. Now, if, let's just say for a given second, all of helium's electrons are over here. That makes this side we call partial negative. So we use this little symbol delta, meaning a partial charge. This is not an ionic charge, and a full charge is partial, meaning it's a little bit negative over here. Why is it negative over here? Well, because I've got electrons hanging out over here, right? And electrons are negative. Now look at this side now. If electrons are just so happen to be hanging out on this side, this side over here is left without electrons. So it's now a little more positive than it used to be. And then let's just suppose that the same thing is happening to this helium atom, where I've got electrons hanging out on this side, meaning this side is a little more negative and this side's a little more positive. So now I have this interaction here between this partially positive side of this helium atom and a partially negative side of this helium atom that creates this little ionic interaction. But it's only for like a nanosecond, a microsecond. This very small, just so happens to happen kind of thing is called a London dispersion force, or van der Waals force. It's a very, very weak attraction because it's momentary. It doesn't exist all the time. It's just really, really short. This happens with atoms. Okay, so this is just atoms hanging out. We're not bonded together. And you can tell that your forces actually get stronger with the higher molar mass. So with helium, I only have 2 electrons in which this is happening. Right? There's only 2 electrons in which this is happening. But let's say I increase to neon. Now neon has 10 electrons, so now I can have opportunity to have, opportunities where I've got 3 over here, 7 over here, and I've got, 10 over here, 0 over here. I have all these different interactions these combinations I can come up with for neon. So as I increase the size of my atom, I increase the strength of this dispersion force. So as I increase the molar mass, I can increase the strength of this dispersion force. How can I tell that? Let's look at the boiling points. Okay? If you have a strong intermolecular force, you're held together really tightly. So it is much harder for you to boil. Therefore, your boiling point is higher. So if I increase my molar mass, I see that my boiling point is much higher than it used to be. I mean, this is on scale of Kelvin, which is a lot bigger scale, right? So London dispersion forces, so the strength of London dispersion force also increases as we get bigger. Just because we have more opportunities for this weird, like, off-kilter electron distribution thing to happen. We got more chances for it to happen. Okay. Now, the next force is called a dipole-dipole force. Dipole-dipole force means you have to have a polar molecule. So here, London dispersion can be with an atom or molecules that are non-polar. Okay, as soon as you have polarity, all polar molecules have dipole-dipole forces. Look, these are the same partial forces we've seen before, right? But now they're not like half a second. These are permanent. So these are permanent partial negatives and partial positives because this whole molecule is polar. So you've got the oxygen with your negative and the carbon with your positive. So the oxygen up here is attracted, sorry, the oxygen here is attracted to the carbon here because this is negative and this is positive. This is the entire reason any organic molecule does what it does. Okay, this like dipole-dipole, this interaction, this is how you get enzymes and substrates to work together. This is how you get DNA to zip and unzip. It's all of these kinds of interactions. This attractive force between these certain specific areas of molecules allows us to do cancer treatments and all kinds of fun stuff. So it's really getting into the good, cool aspects of chemistry, I think. If you're moving on to organic chemistry, this is going to make a lot of sense. Once you take organic chemistry, you'll see a lot of this come back. So again, dipole-dipole force is a lot stronger than this London dispersion because this is just a momentary version of this. This is a permanent version. So this is a lot stronger, this interaction. So we can tell it's stronger because we have increasing boiling points. So if I increase my boiling point, it means I also increase my melting point. But look at the molar masses, they're about the same. So what's the difference in these two? Well, this one is nonpolar, and this one is polar. Oh, I'm sorry, my boiling points are opposite. Increasing, increasing. What's the difference? This way. Okay. So I'm increasing my boiling point and my melting point, and the only thing that's changing is my polarity, right? Because my molar masses are the same. So it must mean that polar has a stronger force than nonpolar, which is true because this is dipole-dipole and this is London dispersion. So one other thing that we need to talk about before we wrap up, I think, yeah, we're almost done. Before we wrap up is like dissolves like. So polar things dissolve polar things, nonpolar things dissolve nonpolar things. Let's look at these images. Image A, you've got oil and water. Okay, this is a molecular view of this. So you've got oil here and water here. Water is polar. Oil is nonpolar. They don't like each other because they're not alike. So they separate, they don't mix. Let's look at the salad dressing. Okay, this is oil, nonpolar. Water, the vinegar is polar. So oil and vinegar is not going to mix. The same thing happens if you have an oil spill in the ocean, right? So this nonpolar layer is going to float on top, and you're going to have this polar layer on the bottom. So if you have something like salt, something ionic is very, very, very polar, right? So that is going to dissolve in water. It's going to do that. But if you have something that's not kind of dissolving in the water, right, it's probably because it's pretty non-polar like oil. It will not dissolve in water. Right, the last intermolecular force we're going to talk about, this is an IMF, is hydrogen bonding. I put bonding in quotes because it's not really bonding. Bonding is between two atoms in a covalent bond. But we call hydrogen bonding bonding because it's so strong. It's almost like a bond. It is between H bonded to enough, N, O, or F. Okay, you have to have an H bonded to N, O, or F in both molecules in order to have hydrogen bonding. That's really, really important. I'll say that again. You have to have hydrogen bonded to N, O, or F in both molecules in order to have hydrogen bonding. Okay, if I have an H and an O, but they're not bonded together, I will not experience hydrogen bonding. So let's look back really quick. Do you see here how I have an H and I have an O? Are they bonded together? No. This is dipole-dipole. It's polar, but it is not hydrogen bonding. Okay, formaldehyde does not have hydrogen bonding. Hydrofluoric acid does have hydrogen bonding. It is only an H bonded to an F. Okay, this alcohol, this OH right here, has hydrogen bonding. So the reason why it's just fancy, it's fancy, strong dipole-dipole interaction. This is a really strong dipole-dipole because the electronegativity differences between hydrogen and NO or F is so great. So like in dipole-dipole, this is a little negative, this is a little positive. In hydrogen bonding, this is really negative and this is really positive. And so that just creates a much stronger interaction here. That's it. It's just a fancy, very, very strong dipole-dipole interaction. So if we look here, you can see, again, we're kind of keeping the molar mass the same, but the big, big, big differences in our melting points and boiling points if you have hydrogen bonding versus something that's only have London dispersion forces, right? This nonpolar molecule only has London dispersion. This is our special bond right here for hydrogen bonding. Just way, way, way different. I have seen questions that will ask you to identify hydrogen bonds. This is not a hydrogen bond. This is a covalent bond between oxygen and hydrogen. This is your hydrogen bond. Okay, this is a covalent bond. This is your hydrogen bond right here. It is between the O of one water and the H of another water. But notice, both molecules have to have H bonded to NO or F. H bonded to enough has to be NO or F, or you can't have hydrogen bonding. Again, this is what allows DNA to do its thing. So in order for DNA to unzip, something comes along and it breaks these hydrogen bonds. And for DNA to come back together, it just kind of relaxes and it comes back together automatically because of these really special hydrogen bonds we see between the groups here. The last really quick thing is called ion dipole forces. Look, this is just what happens when some water dissolves something. So you've got this dipole from this polar water molecule, and you have an ion. Notice how the water arranges all of its positive hydrogens close to the negative chlorine. And notice how water arranges all of its negative oxygens close to the positive sodium. That's it. It's just talking about the interaction between ions and the dipoles. They're just going to arrange themselves in a way that makes sense. Okay, here's a table of all the forces we just talked about, and email me if you have any questions about any of this, and I hope that you have a good day.